Next, the fourth one. Explain the following statement clearly. To call a dimensional quantity large or small is meaningless without specifying a standard for comparison. And the reason for that statement is clear, and we write that reason here. Let's see what I have written. This is because the reason for that statement is this. We can only use the words large and small with something. Say you want to say a large table or a small room with something in relation to something else. Simply that saying that something is large or small does not really convey any information. Simply saying, for example, that an atom is small doesn't mean much. We can instead say that an atom is much smaller than a pen, say a marker pen, or that an atom is larger than an electron. So when there is nothing to compare it to, then these words don't really mean anything. You see that this object, an atom, you are using the word smaller with this object. If you just simply say a small atom, that doesn't really mean much. But smaller than a pen, then there is a comparison. That means something. Okay, and especially we are talking about dimensional quantities. So obviously comparison is necessary, means it's essential. Whereas you can also use the word large even with an atom. An atom is definitely larger than an electron. So there the comparison has changed. The other object is now much smaller, so this also is meaningful. And the exercise doesn't end there. Now, in view of this, in view of that statement, reframe the following statements whenever necessary. There are some statements. The first of them is this. Again, here it's about atoms. Atoms are very small objects. This needs reframing because here we are using the word small without anything else to compare atoms to. So we can reframe this statement like this. Atoms are very small, of course, but compared to everyday objects, for example, a pen, or even an object as small as a grain of sand, or even cells in our bodies, atoms are much smaller than them. Cells, however, although they are everyday objects, but we do not see them with our naked eyes. Their sizes, that is sizes of atoms, are typically of the order of 10 to the power minus 10 meter. Okay, so here you have a kind of quantitative measurement. Here also we are actually comparing with the unit meter. Next statement, a jet plane moves with great speed. Again, this also needs reframing. How great is the speed? So we can reframe this statement like this. A jet plane moves at a much higher speed of about 900 km per hour than, say, an ordinary car, compared to an ordinary car, which moves at an average speed of about 50 km per hour. Average speed, if you are thinking of top speed, maybe it is 100. But the point here is that a jet plane moves at a speed which is much higher than how fast ordinary objects move that we see around us in everyday life. Next, we have this statement, the mass of Jupiter is very large. Again, this also needs reframing. Large means how large? So the reframing can be done in this way. We can compare the mass of Jupiter with the mass of our planet. The mass of Jupiter, which is about this much, 1.898 times 10 to the power 27 kilogram, is much greater than the mass of Earth. And the mass of Earth is about this much, 5.972 times 10 to the power 24 kilogram. If it does not look like much of a difference, you do not look at these numbers, 1.8, 5.9, you look at these powers of 10. Here it is 24 and here it is 27. 3 orders of magnitude higher than the mass of Earth, approximately. Next, statement D. The air inside this room contains a large number of molecules. This one also needs reframing. Large means how large? So the reframing can be done for this one like this. The air inside this room contains a large number of molecules, about 10 to the power 26. These are only rough numbers, okay. They give us a rough idea of about how many molecules you can expect to have. And that too, this number you can understand depends heavily on many other things, temperature and pressure, to name only 2 which are immediately obvious, but there will be other things also. But anyway, it's just, it's about 10 to the power 26 or 25, 27. Compared to what? That's what matters. Compared to the number of molecules in, say, a small drop of water. When water is dripping from somewhere, those small drops we are talking about here, and that number is about 10 to the power 21. So you see that it's really, the difference is orders of magnitudes more. That means this one is 5 orders of magnitudes more than this one. So you have to multiply this rough number by 10 to the power 5. That many times more if this one is than this one. The next statement is this. A proton is much more massive than an electron. Yes, this does not really need any reframing. Although we are not saying exactly how massive, or we are not quantifying the difference, but we are giving a comparison. So that is why this does not need any reframing. You can see, if you want to say something more, you will give a number. But the way we are stating this, that is okay. And the final statement is this. The speed of sound is much smaller than the speed of light. This one also does not need any reframing, although we are not quantifying here how small. And you understand, you already know that speed of sound and speed of light are slightly different in nature. This is constant. This, however, depends on many factors. In dry air it is one, in wet air it is something else. There are many things, but the framing of this sentence is okay. Now if you want, you can put those more restrictions. The speed of sound in dry air is much smaller, but this much smaller. So those are the extra pieces of information.